So, let's see what we got. Actually, this is good information to have for tomorrow's lab because you'll be doing this. Coming up with the rate law constant, or not, well, that too, but you'll be coming up with reaction orders using this approach. Tomorrow, by the way, we're supposed to get some snow changing into kind of ice or freezing rain, but I think it's supposed to be early. So just kind of keep an eye. Remember, I commute from Burlington, so if the roads are tricky, I will definitely send everybody a message via email and tell you we're not having lab tomorrow. But hopefully we will. So one more way of coming up with those reaction orders, and it is by the method of initial rates. So, for instance, we've been talking about if you have this reaction where you have two reactants, A and B, and the little a and little b are the stoichiometric coefficients, you could come up with the rate law expression looking like this, where K is the rate law constant. Of course, this is the molar concentration of A raised to its reaction order, molar concentration of B raised to its reaction order. And I meant to bring my, if you have your law of logs sheet, you might go ahead and grab it. One of the things we know we can do is we can apply the log to both sides. Now, ln is a natural log and log is log base 10. The base for the natural log is like this e. So anyway, we'll kind of be talking more about this. We could have done the log or ln. But one of the things then is if we have the natural log of this quantity, where basically we have three things multiplied by each other. K, molar concentration of A raised to its reaction order, molar concentration of B raised to its reaction order. We can break it out into basically the natural log of these things added to each other. So, for instance, if I'm going to go ahead and change the initial concentration, that's what the subscript 0 means. If I'm going to go ahead and monkey with the initial molar concentration of A, but if I'm going to hold B constant, we did this before. B actually is going to be along for the ride, the molar concentration of B, because it's held constant. So since B is going to be held constant, I'm just going to go ahead and stick it in with my rate law constant. Okay, so it's not going to change. What is going to change is the molar concentration of A. The initial molar concentration of A is going to change, and as it changes, we're going to see a change in the initial rates. Okay, so that's why I set it up this way. Now, we actually applied one log the other day where if you take the natural log of quantity raised to a power, here in a minute you're going to see we can take that power out. And that's why we use log. That's why we use logs like that. So I can rewrite this to say the natural log of the rate, right, at these different initial concentrations of A, will equal to M now is the reaction order of A, okay, times the natural log of the initial molar concentration of A. Again, B is going to be held constant, so that's why we kind of put it over here. We're trying to get it to something that we can plot. So if we plot along the y-axis, the natural log of rate, and if we plot along the x-axis, the natural log of the initial concentration of A, then the slope, isn't this funny? The slope will be equal, M is equal to M. The slope is equal to the reaction order, okay? Or I should say the slope is equal to the reaction order. So that's kind of cool. That's what you're going to do with your data from tomorrow. So this kind of shows you, again, if you have that sheet I gave you the other day with logs, like we did just a minute ago, if you take, whether it's a natural log or log base 10 of a product, things multiplied by each other, we can break them out as the natural log of the individual components added together. That's exactly what we did. And then we use this, made use of this fact again. If you take the natural log or the log base 10 of something raised to a power, that's equal to that something times the natural log of the base. Okay, yep. And in this case, we're holding B, the molar concentration of B constant. So yeah, what we should be able to do is plot along the y-axis the ln of the rate, and along the x-axis we should be able to go ahead and plot the natural log of the initial molar concentration of A. It should give a positive slope, and that M is going to be equal to the reaction order of A. And then, since we had two reactants, actually, you guys could do this tomorrow, we could change it up. The thing that's different here, if you read it a few times, is then we're going to hold A constant. And since we're holding A constant, we would go ahead and put it with our rate law constant over here, and we're going to vary B. And in this case, we could go ahead and plot, again, the natural log of the rate. When we're varying B, in this case, the natural log of the initial concentration of B, and we're going to get a positive slope, and that M is going to be equal to the reaction order of B. That's it. But wait, there's one more. I feel like I'm on a commercial where they keep, but wait, if you order now, we'll throw in, just pay separate shipping and handling. Okay, it's one more cool thing, and you guys are going to do this with your data you get tomorrow. Well, let's just say now we know our reaction orders. We can do one more plot, and basically we go back to our rate law expression or rate law equation. Now again, we know M and N because we got it from earlier graphs. We literally can plot rate along the y-axis, and then what you see in kind of in the arrow along the x-axis. So this isn't the natural log of rate, this is simply rate. And for ours, we would plot the molar concentration of A raised to its reaction order, we now know, times the molar concentration of B raised to its reaction order. We should have a positive slope, and the slope then, M will be equal to your rate log constant, K. So 3 graphs. Everything you want to know about that equation. It's funny, if I was getting ready for a test or trying to digest this material, you know, I would kind of get these in my notes or try to internalize them. These have positive slopes, don't they? Not all physical plots like this would have positive slopes. So I have an example. You're going to see actually 4 trials where oxygen, the O2, initial concentration of O2 is held constant, varying the initial concentration of NO, and then 4 more trials where this is held constant, and we're going to vary the concentration of the O2. And we're going to look at the effective rate, and we're going to do exactly this. The first 4, like I said, we're going to hold O2 constant, vary NO, and varying NO, we're going to be able to get to the reaction order of NO. So here we go. Looks like a busy slide, but you can see where these are held constant, these are held constant. 8 different trials. So if we take the first set, take the natural log of that, take the ln of this, and take the ln of these, we basically have this plot. For the second one, we're going to take the ln of this and the ln of this to get the rate log constant with regard to the O2. Okay. A graphical approach to determine the reaction order, and then ultimately the rate log constant after we know the reaction orders. So these were the values we saw for the initial concentration of NO. O2 is held constant. These were the observed rate. Take the natural log of the rates, it's going to go along the y-axis. The natural log of the molar concentration of NO is going to go on the x-axis. And voila, it looks like this. So we're dealing with reaction orders that are 0, 1, and 2. I think I kind of narrowed it down that. In this case, it's always kind of fun. You're like, oh, well, 1.99, I bet that's supposed to be 2. So the reaction order with regard to the NO is 2. And then this is looking at the second set of 4, where we massage the data. I have to take the natural log of O2. That's go along the x-axis, the natural log of rate, go along the y-axis. Positive slope. And we look at the slope, and it's 1.02. I'm thinking that's close enough to reaction order of 1. So now we can go back and plug those into our rate law expression, where the NO is second order, the O2 is first order. Now let's go for the K. So to go for the K, like what you're going to do with your data that you put out tomorrow, is we're going to take all 8 trials. Oh, before I do that, so the overall reaction order is 3. Remember, the overall means we're adding the reaction orders of 2 plus 1 is 3. And remember, one of the things that's important about overall reaction order is it sets the units for K. In order to get the rate, we want moles per time, molarity per time, moles per liter per time. And so K kind of has to clean up the molarity introduced by your by the other 2 terms. So yeah, we're going to look at all 8 trials, and then rate is going to be just rate along the y-axis, like we said, and along the x-axis is going to be kind of the heart of the rate law expression. In this case, we're going to take the molar concentration of NO squared times the molar concentration of O2 raised to first power, because NO is second order and O2 is first order. And we get these values as we go along the x-axis. So oftentimes it kind of takes on this sort of paired appearance, paired as in 2, kind of go in pairs. So here are all 8 of those points plotted. Again, now in this case, what the slope's going to do is give us K. And the units for K need to be, what does K be? Units of K will be liters squared per mole squared, also in the denominator time, in this case seconds. Okay. And this is, I was like, now how does that work? Well, this is how it works. If you ever have to kind of think through what will your units of K be, notice that what's introduced by the NO is moles per liter squared. NO squared. What's introduced by the molar concentration O2 is moles per liter. So this blank, whatever it is, needs to be such that we get moles per liter per second. So in order for that to be, we basically have to have moles squared at the bottom, liters squared on the top. No. Yeah, because that's squared. Yeah, liters squared on the top. Moles squared on the bottom, liters squared on the top, and seconds in order to get what we need to get for our rate. Okay, so you guys already handed in the homework. That was for today. Perfect. So let's see how far we get down the road into part 3. Dun, dun, dun. Erase the board. So in what we've been looking at are basically initial rates, basically running several experiments and varying the concentrations to see what effect it had on the initial rate. This changes it up. Basically, and if you're kind of a visual person, like I am, I think of it this way. This is one run, and so basically we have for one run the time and the molar concentration of a reactant. We'll just call it A. So we have time, And of course, we know the molar concentration of the reactant is going to decrease one run. And we check it out. We see what we can get from that one run. And ultimately, we're going to be able to get to reaction orders and rate law constants too. But there's definitely a difference. Concentration versus time. That's exactly what I drew up here. Concentration versus time. The concentration is measured as a function of time. And how this behaves, it's kind of a decay process because you figure the molar concentration of your reactant keeps decreasing, so it's kind of like a decay process. How it responds actually is a function of its reaction order. I'm gonna show you tricks for zero order, first order, and second order with time concentration data. Yep, and if you can plot this, like you're gonna need to be able to plot it for homework and also be able to kind of think about a plot for for homework and on the test. If you can identify the zero first or second, then also you can pick off the K from your plot as well. So let's start with zero. And you know, I go for several months, like a year between teaching this, and so sometimes I have to kind of brush up on it too. So anyway, so zero order, we said that if a zero order means that rate is equal to K, I think it's coming up here, raised to the 0th power. That means that this is always 1. That means the molar concentration has no effect. Zero order. So if that's 1, then our rate is equal to K. Your rate is equal to your rate law constant. It's kind of weird, isn't it? So for zero ordered, we can come up with this time concentration equation for zero order, where A0 is the concentration you started out with, and A, or molar concentration of A, is the concentration that A is at time t. See how that works. So I'll start a little thing here. You know, and if I was you never know what to write down, what the teacher writes on the board, but I would probably write this down. Zero order, the time concentration equation looks like this. Molar concentration of A at time t minus the molar concentration of A that you start with, or A0, is equal to negative KT. Oops. So rearranging that, we get molar concentration of A at time t is equal to negative KT plus the initial molar concentration of A. Now, the reason we would do that is because we're trying to get it into a form of something that we can plot. So if we plot, and I'll add this to this over here, for zero order, if we go ahead and along the y-axis, we simply plot the molar concentration of A at time t, and along the y-axis, we simply plot time t, okay? That actually should give us a negative slope. And in that case, the slope of your line will be equal to negative K. And that's it. Zero order. It's a test. So I said we're going to do 0, 1, and 2. So let's take a look at what first order looks like. Oh, before we do that. So notice what we're doing here, what somebody's doing here, is looking at the decomposition of tungsten, decomposition of silicon dioxide, And the one that's, and here along the y-axis, we have the molar concentration of ammonia versus time. So, I see. Decomposition of ammonia, whether it's occurring on tungsten or whether it's occurring on silicon dioxide. The one with the straight line, this top one actually must be zero order. This one, though it has a curve to it, is not zero order. That's how that works. You just have to match up what was plotted. It's a zero order test. Straight line, it must be zero order. This one, no. That's what we mean by the test. All right, how about first order? Well, first order means that the rate is equal to K times the molar concentration of the reactant raised to the first power. Okay. To try to get that into a form that actually we can use as a time concentration calculations, and also get ready to be able to plot something using calculus, this is what it looks like. So first order. Jeez. First order, the natural log of the ratio of the molar concentration of A at time t to the molar concentration of A that you start with. And that's going to be equal to negative KT. And actually, for first order, this is a time concentration equation we can use later too. That to me is not ready to plot. Let's go ahead and flatten it out. I don't know, do I put this one there too? No. One of the things, it's another trick about the law of logs. We said if you're multiplying things together, you can break it out as the things add the quantities, natural log of the quantities added together. That sheet I gave you the other day said if you're taking the ratio of them, you can break them out and they're equal to the difference. So it looks like this. This guy can be broken out into the natural log of A minus the natural log of A0. Oops, sorry. A0 equals negative KT. And you see all that is done down here is to drag that second term over to the other side. To get this. Now that looks like something we can about plot, doesn't it? If we kind of put underneath there y is equal to mx plus b, what we've got now is to test for first order, we can go ahead along the y-axis, plot the natural log of the molar concentration of A at time t, and along the x-axis, go ahead and plot time, or t. We will have, again, a negative slope, and the slope of the line will be equal to negative k again. That's it. That's it, man. I think I have an image from OpenStax to kind of show you this sort of test. Oh, it's pretty straight. And sometimes you're like, oh, it's a little curve to it, I don't know. But if we have the correlation coefficient, you can see, remember, the closer it is to -1, the more that likely it is a straight line. So this is the decomposition of hydrogen peroxide. Must be, looks like first order to me. Not so much. Okay, so the decomposition of, or this is not decomposition, this is a dimerization of C4H6. See a little bit of it's a natural log. Now, we could have gone ahead and instead of taking natural log, we could have tested for zero order and seen if it was a straight line. But I don't think it's going to be. So the last one I want to do is second order. And for second order then, the rate law expression would look like this. Go ahead and integrate it, calculus, and come up with this relationship for second order. So the inverse, or 1 over the concentration of A at time t minus the inverse, or 1 over the concentration of A at the initial molar concentration of A is equal to, now in this case, it's a positive rate law constant T, positive KT. Don't have to do too much arranging to get something that we can plot. Here's something that we can plot. We're going to go ahead and put y is equal to mx plus b. Where in this case now, if we plot the inverse of the molar concentration of A, or 1 over A, and along the y-axis, and time, or t, along the x-axis, you should get a straight line. In this case, it'll have a positive slope, and the slope of your line will be equal to your rate law constant k. So that's how that works. That's it, Mom. So again, the dimerization of C4H6, and I'm liking it. So if you're like, well, which test are we testing for? Well, look what's plotted along the y-axis. We have the inverse of the molar concentration, so this means to be testing for second order. Pretty darn straight, so I'd say the second order. So you could run into a problem like this, where we have the nitrogen decomposing to form NO and O2, sorry, nitrogen. NO2 decomposing to form NO and O2 at a specific time or temperature of interest, 300 degrees Celsius. Okay, so there is our time concentration data. What I usually do with something like this is to go ahead, you've seen me do this before, write the generic sort of rate law expression. It just makes me feel good about it. So I'd write rate is equal to rate law constant K times the molar concentration of NO2 raised to the M power, where M is the reaction order. So I just do it. So the molar concentration, not so surprising, of the reactant decreases over time, decays over time. So what you're going to see in the next few slides is we're going to test for zero order. So this will be zero order test, a first order test, and a second order test. It's pretty easy to do with Logger Pro. So. And then whichever one's straight, we're going to go ahead and pick off the slope to say what the rate law constant K is. Suspense is killing me. So you can see as far as coming up with calculated columns, of course, the first two columns are not calculated. They're our raw data, time and the molar concentration of NO2. The natural log of NO2 getting ready for the first order, the inverse of NO2 getting ready for the second order. So, not so straight. This must be a zero order test, simply the molar concentration of NO2, not straight line. It fails the zero order. Getting more straight, but I definitely still see some curve here. The fact that the person who drew this line didn't come up with a correlation coefficient. Correlation coefficients are associated with just straight lines. It means that it's not a straight line. So this is the natural log of the molar concentration. That must be first order test. It fails that one too. So this one passes. Remember, for a second order, it's going to have a positive slope. A correlation coefficient looks like it was dry lab to me. Okay. Correlation coefficient looking great, so that means that the slope, which is 0.537, would actually be the rate law constant K. So it passes that line. Just pick off the slope, and that's your K. Okay? And since it's second order, then your units of K, and there's only second order overall, will need to be liters per molar. Like we talked about before. I really like this table. I think they did a good job with this table. The columns are 0, first, and second order, and it's stuff we've already talked about. So like the rate law expression would look like this. If you have a reactant A, the rate for 0 order would just be equal to K. For first order, it'd be K times molar concentration of A. For second order, K times molar concentration of A raised to the second power. The units of the rate law constant then are set by the reaction order also. So they're given here. We talked about the integrated rate law equation over here. So how do we do a check? How do we plot for them? Or yeah, do a check to look for 0 order, first order, second order. Exactly what we talked about this afternoon. How do you find the K? Well, in the case of the 0 and first order, it's negative slope. And in the case of second order, it's equal to the slope. Now this one we'll be talking more about next week. Remember, we don't have class on Friday. Okay. Talking more about half-life. All right. So, what if you have more than one reactant? How can you do a time concentration to make that work for you? Well, the answer is to basically OD the system on one of your molar concentrations, so the change in it is basically 0 over time. So in this P stands for kind of like a, well, in this case, the P is going to be where we're going to dose it with extra amounts of B, the reactant B, so this won't change. The molar concentration of B will basically be constant over time. If we can get B constant over time, I talked about this the other day, where K prime here is what we call pseudo constant, where it incorporates B, which is constant. So we add it. And actually, this is a technique we're going to be using for a week from Thursday. We go ahead and have the system OD on B. So the example we're going to do is, what if A, and we do care about the changing molar concentration of the reactant A, it's going to decrease from 0.001, 0.0 molar, pretty low. What if we go ahead and make B pretty high in its initial molar concentration? Then that means actually at the time that all A, and it's assumed that they react in a one-to-one stoichiometry, at the time that all of your A is then converted to products and a certain amount of your B is used, notice that the amount of your B that's used is essentially 0, especially when you take into consideration you have to round according to decimals because you're subtracting. So it's basically unchanged. So that's what I mean by you have a system OD on B. All right. So this will be due on Monday, Marvelous Monday. That's a short section. Cool. So we'll see everybody tomorrow. Let's see. Oh, anyway. Come and run the lab.